Good morning, everyone. My name is Aditya Sharma, and this is uh, Advanced Thermodynamics and Combustion being conducted by IIT Guwahati under NPTEL program. And this is the fifth live tutorial session in this series of 13 such sessions. The instructor for the course, as we all know, is Professor Niranjan Sahu from Department of Mechanical Engineering, IIT Guwahati. And I am Aditya Sharma, a Prime Minister's Research Fellow, also from Department of Mechanical Engineering, IIT Guwahati. So we shall be starting in another couple of minutes. So let's wait for another 5 minutes and then we can start today's session. Okay, thank you. Okay, so I believe we can start today's session. So the theme of this week also is thermodynamic property relations. Okay, so in the last week's lectures, we saw the phase change processes. So uh, equations like Clapeyron equation, right? And Clausius-Clapeyron equation. These two equations are related to phase change processes we saw in the last week's lectures. Okay, so in this week's lectures, we continued that theme only, that is thermodynamic property relations. So the main idea is that we should be able to get different properties linked to a particular system. Okay, so in that effort only, in the last lecture we saw when there are phase changes, how the properties change. And in this particular week's lectures, we will be seeing uh, how we can calculate the heat capacity of a fluid of a system, right? In lecture 13, we saw that. Then we have in lecture 14 discussion on throttling process and then liquefaction of gases, which comes out of throttling process only. So in these topics also, how the properties change and how we can use the relations, 16 relations we developed, right, in the previous lectures. So how we can use that. So we will be seeing all that in this week, right? Okay. So the scheme of the session will remain as it is. First, we will be seeing the topics that have been covered in this week's content, and after that, we shall see conceptual questions. And at last, we will be solving some numerical questions. Okay. So let's go through the topics that have been covered in this week's lectures. So first topic is evaluation of property change. So uh, this heading basically is the revision. Sorry. So this heading basically is the revision of the previous uh, relations that we developed. Okay. So be it basic relations, be it Maxwell relations, or some additional relations, right? And then there is Clapeyron equation, and then there is Clausius-Clapeyron equation. So all this we have seen in previous lectures, and this is the revision of this heading is the revision of all those things. Okay. Also in this evaluation of property change, this two new properties. Two properties have been mentioned. One is your isothermal compressibility, and then is your volume expansibility, right? And also two more properties are also there. One is isentropic compressibility, and then speed of sound, right? So I'll just write their formula, right? So this is kappa, that is isothermal compressibility. This is minus 1 by v dou v by dou p at constant t. Then we have volume expansivity. That is 1 by v dou v by dou t at constant p. Okay. And then there is alpha, that is isentropic compressibility. So this is at constant s. Then there is speed of sound also, which is Okay, so these four properties have been mentioned in this evaluation of property change. Then we saw that how we can define different properties, right? So on the basis of, there are two cases on the basis of temperature and specific volume. This is one case where on the basis of temperature and specific volume we can define the properties, and then second case is temperature pressure, in which we can define the properties on the basis of temperature pressure. So these any of these two, if you take one at a time, in that case and also if we consider these as independent properties, so other properties we can uh, evaluate from the set of two these properties, either a temperature, a specific volume, or temperature pressure. Okay, all right. So in the temperature, this temperature case one, temperature specific uh, volume case, we saw how we can derive the entropy change and then this internal energy change. Okay, so if you see entropy change can be written as, so this is case one, right? So I'll just not write the heading, just I'll plainly write the relation. Okay, so entropy change in case one, it can be written in this way. It's integral form. How it has been derived, all this has been covered very well in the lectures. I'll just jot this down so that we have context for our future discussion in case this has to be used in future discussion, right? And then there is this relation on internal energy change. So we shall briefly go through the things we have covered in this week's lectures. Just jotting it down so that we have context of what has been covered in this week's lectures. So this is for case one, that is temperature specific volume, right? And then if you see the case two, where we have taken temperature and pressure as the independent properties. So in that case, we have evaluated the entropy change and enthalpy change. And when we derive these two, so this is for entropy change, expression for entropy change, and then for enthalpy change, we have expression this. So this is about these two cases. Okay. Then the next heading is internal energy change, right? So here we saw that the internal energy change can be derived from this TDS relations, right? And then there are two ways using which we can derive these internal energy equation, right? Okay. Then after this internal energy equation, we saw the construction of property tables in this lecture 12, right? So we have here a temperature versus specific volume diagram, right? And in this diagram, we see that how the property tables are constructed, and this has been explained using this particular diagram. Okay, this is in slide 11 of this lecture 12, right? And then whole the process has been enlisted in this page 12 of lecture 12, right? So this is about construction of property tables. Okay. After that, moving on to lecture 13. So these two lectures from here onwards, these two lectures are of importance. So first is your lecture 13, which is on heat capacity equations, right? So first heading in this lecture is fundamental thermodynamic equations. Okay. So these fundamental thermodynamic equations are the same as we have been seeing in the previous lectures: basic relations, Maxwell relations, additional relations, phase change processes. Like we defined Clapeyron equation and then Clausius-Clapeyron equation for phase change processes in the previous week's content. And then there is a single phase systems that we just saw in lecture 12, right? And then after that we saw the internal energy equations. That is the second heading in lecture 12. So these equations have been enumerated in this fundamental thermodynamic equations heading. Right? Okay, so then we move on to heat capacity equations. Okay, so heat capacity equation. So in this we discuss how we uh, develop heat capacity or get heat capacity from laboratory measurements, right? In that discussion, we saw that because of thermal expansion, right, it is difficult to get the specific heat at constant volume. And in that case, uh, what we do is that we normally focus on the heat capacity at constant pressures, right? Okay. And then one point in this uh, heat capacity equations discussion is that the relation between Cp and Cv we call as a Mayer equation, right? And then various points can be deduced from this Cp-Cv relation, right? Heat capacity at constant pressure and heat capacity and constant volume relation. Various uh, deductions can be done on the basis of the relation of these two properties, right? Right. So, for example, isothermal compressibility is positive for all the substances in all phases, right? And then if these two specific these two heat capacities have to be equal. In that case, what case is to be there? One case is that your temperature should tend to zero. So if Cp has to be equal to Cv, in that case, your temperature, either temperature tends to zero, or second case is dou V by dou T at constant pressure tends to zero. Right? This. Okay. So these two cases for Cp equals to Cv are there, right? And then specific heat ratio has been discussed, right? That is Cp by Cv. Okay. So all this has been discussed in this heat capacity equations. Then comes your TDS equations, right? Temperature and entropy change equations. So in this topic, we study two cases. One case is the effect of reversible isothermal change of pressure for pure substances, right? So what we are doing, we are keeping the conditions as reversible and isothermal, and then we are changing the pressure. And then second case is the reversible adiabatic change, right? So the process is reversible, the change process is reversible, and then also it is adiabatic. And in that case, if we change the pressure of a pure substance, so how it fares, all this has been discussed in this particular heading, right? For example, so the reversible adiabatic increase in pressure will produce increase of temperature, right? In case we have volume of expansivity, the value is positive. So if beta, that is volume of expansivity, is positive, in that case, increase in pressure will produce increase of temperature, right? So all these types of discussions have been done in this heading, right? So this is about TDS equations. Then we saw last lecture of this week's, right? So in this lecture, first we saw fundamental thermodynamics equations. That is same as was with the uh, last lecture's first slide, right? So all the fundamental thermodynamic equations that we have derived, all this has been enlisted in this particular heading. Then we move on to throttling process. Okay. So what is throttling? This is very interesting and important. So if you see your lecture's content, so it says that when a fluid passes through a restriction, its pressure decreases, right? And this phenomena is known as throttling, right? Okay. So later, what we do is, so we define this. So with this throttling process, what happens is that your temperature changes, right? And this temperature change with the pressure change, right? Because we are saying that when the fluid experiences a restriction, the pressure decreases, right? And with this pressure decrease, there is a change in temperature, right? And then to uh, relate change in temperature with the change in pressure, right? So to uh, define that, we we take the help of Joule-Thomson coefficient. Okay? So Joule-Thomson coefficient is nothing but it is also written as mu j, right? So mu j is dou T by dou P at constant enthalpy. Right? So the Joule-Thomson coefficient is defined at constant enthalpy. Right? So when we consider a throttling process, what we take into consideration is that the enthalpy of this fluid remains constant in this whole uh, process of state change. Okay, so whatever device is making this change happen, that we define as an isenthalpic device. Basically, this is the meaning of it. So let's see this. This is important because so let's I'll draw this temperature versus pressure diagram. Okay. So if we have to define the draw the throttling process, so it will be something like this. So we start from here, right? So these are all these curves are for different processes, right? This is not for a single uh, process that is making this change happen, right? So these curves correspond to different processes. But if we take one curve at a time, right? One curve. So we call this as inversion curve. So if you take one curve at a time, so we start from here, right? Right hand side of this curve. Right? So in starting we have some pressure, right? This pressure. And then if we use the throttling process, in that case the pressure decreases, right? So this moves in this direction, the curve moves in this direction. Okay, then if we see the curve, we can see that initially the temperature increases in the curve, right? But then there comes a point from where this temperature starts to decrease, right? So the point up to which this temperature keeps increasing while the throttling process is ongoing, right, is known as inversion state. Okay, so this is your inversion curve. And then if we take the slope of this curve at any point on the curve, that basically is the Joule-Thomson coefficient, because all these curves are isenthalpic. That is, the enthalpy remains constant in all these curves. Okay, so So inversion state we have discussed, inversion curve we have discussed. Then there is one more term, that is maximum inversion temperature. So this inversion state gives you inversion temperature. Okay. So if we have this as our curve 1, then this is inversion temperature T1. Okay. So this is inversion temperature. Then, so for different curves, different isenthalpic curves at different temperatures, if we see, so there are different inversion temperatures. So I'll just extend this y-axis. So let's say this is our let's say this is our maximum inversion temperature. So what it tells that, so as we move upwards in this curve, right? So the temperature of the initial temperature of the fluid is increasing. Okay, but then there is a point beyond which if we move, so we won't get this dip in the left side of the inversion state because we won't reach the inversion state, right? If the initial temperature of the fluid is higher, right? So, so let's say this is curve number 5, right? And this is curve number 4. So if fourth curve is our curve that gives us maximum inversion temperature, right? So beyond this, if the fluid's initial temperature is higher than this, in that case, we won't be able to get a uh, dip in the left side of this curve beyond the inversion state. And the disadvantage of that is that we won't be use such a process for liquefaction of gases, right? Because this left hand part of this curve, right, left to the inversion state, this particular section is the one that we use for a liquefaction of gases, because in this case when we are throttling, the temperature of the fluid is decreasing, and this decrease in temperature is used to liquefy the gases. So this is the whole idea of this liquefaction of gases, right? So with this I also discussed the liquefaction of gases. So I discussed Joule-Thomson coefficient from this graph only, and then what is an inversion curve? I was just discussing the inversion curve only, and then what is liquefaction of gases? This I discussed. So these are the topics that have been covered in this week's lectures. Okay. So now moving on to the questions. So this is our first question. Let's try to answer this. Okay, the first question says that in a single phase region, any one of the three parameters can be regarded as independent property to fix the state, whether this question is correct or not. So, to define a particular state, it is important that we have at least two properties. Okay. So, in the lecture 12, we saw that it can be either temperature and specific volume or temperature of and pressure. So, these two properties, independent properties, we use to fix the state. Yes. So, in that case, so this becomes a false statement because it says any one of the three properties, any two properties we require. Okay. So moving on to next question. So the topic of this question is the evaluation of property change from lecture 12 only. And the question says that by considering temperature and pressure as independent properties that fix the state, the change in internal energy and enthalpy, right? So because it's du in itself is changed, so in is not required. So change du and dh is associated solely with pressure, specific volume, temperature, and specific heat capacity at constant volume. So whether this is correct or not. Please try to answer this. Okay. So if we see our this lecture 2's discussion, in which we discuss the evaluation of property change based on temperature and pressure as our independent properties that fix the state. So here we have done this discussion that this change in entropy and change in enthalpy can be associated with this pressure, specific volume, temperature, and then specific pressure. Because if you see, this is question number. Here we see that change in entropy is written as this. Okay. Also, we have written this. So we can see here also these two expressions. So these are from this case through discussion of temperature and pressure. So change in entropy and change in enthalpy are dependent on pressure, volume, temperature, and specific heat capacity at constant pressure. Right. So from this only it can be answered. So though Cp and Cv are can be linked to each other, but from the context of this discussion that we have done on temperature and pressure, it has to be linked with the specific heat at constant pressure. Okay. So in that case, B option is correct. Okay, so moving on to next question. So this question again is from evaluation of property change, and it states that the specific internal energy can be calculated from specific enthalpy using equation this U equals to H plus PV. So whether this statement is correct or not, we can try to answer this. Okay, so if we have the specific enthalpies value, from that we can calculate the specific internal energy, right? But then the statement says that it can be done using this equation. This is U equals to H plus PV. So whether this is correct or not. So if this equation is correct, then the statement is correct. So if you carefully see this equation, right? So whether this is correct or not. So this has been given in slide 9 of your lecture 12. Okay. So this equation basically is H equals to U plus P. Okay. So this can be done. Specific internal energy can be calculated from specific enthalpy. But then the equation is this and not the one given here. Okay. So in that case, this becomes a false statement. Option B is correct. Okay. So moving on to next question. So this question is on heat capacity equations. So this is from lecture 13. The specific heat at constant temperature, that is Cp, is difficult to acquire due to difficulties in experimental measurement of volume expansion. Whether this statement is correct or not. Please try to answer this. So this should have been actually thermal expansion. So sorry for this. So the question is, the specific heat at constant pressure is difficult to acquire due to the difficulties in experimental measurements in the presence of thermal expansion. So whether this statement is correct or not. Now please try to answer this. So this is a false statement. Why so? Because this difficulty that the statement is talking about comes in picture when we have to find out the specific heat at constant volume. Okay. In that case, this thermal expansion comes into picture, right? And because of this difficulty in experimental measurements in the presence of thermal expansion, it is difficult to get this specific heat at constant volume, right? So had the questions said that the specific heat at constant volume is difficult to acquire, so this would have been a valid statement. But that is not the case. In that case, this becomes a false statement. Okay. The general relation between Cp and Cv is often referred as. So this I have already discussed, already mentioned in the topics discussion. So Clapeyron equation we know is for phase change processes. Last year's Clapeyron is also for that only. Joule-Thomson is for throttling process. Okay, and then the last option left is Mayer option, which is also the correct option. Okay. This should have been D option. Okay. So moving on to next question. The next question again is from the heat capacity equations topic. And this is question number 6. It says that isothermal compressibility is positive for all substances in all phases. So whether this is true statement or not. So first see what is isothermal compressibility. So this is your isothermal compressibility. Minus 1 by nu dou by dou p of nu at constant temperature. This is your isothermal compressibility. So at constant temperature, when pressure changes, with that specific volume change takes place. So is it true that it will be positive for all the cases? So this is a true statement. Okay. The isothermal compressibility is positive for all the substances in all the phases. So this is from your lecture only. Okay. Lecture 13 slides. This is from there only. So isothermal compressibility. So this is a true statement in that case. Okay. So option A is correct. Moving on to next question. So this is question number 7 again on heat capacity equations. It says that specific heat capacity at constant pressure and constant volume are equal when temperature approaches 0 degrees Celsius. So whether this is true or not. You can try to answer this. Okay, so this can be, we can comment on this from this particular statement. This is question number 7. If we see Cp minus Cv, okay, so this is equal to minus T dou V by dou T square at constant pressure, and then dou P by dou V at constant temperature. So in that case, the question says that when the temperature approaches zero. Okay. So if the right hand side becomes zero, in that case we get Cp minus Cv equals to zero. That is Cp equals to Cv. Then these two terms will be equal. That can happen when the T is zero, but T here is not taken in degrees Celsius. It's taken in Kelvin, right? So T has to be 0 Kelvin. But the statement says that when it approaches 0 degrees Celsius, so 0 degrees Celsius essentially is 273 Kelvin. Okay. So in that case, it won't be true for this case that Cp and Cv are equal. So this becomes a false statement. So it's 11 a.m. already, and 1 hour past this session. So we will take a 5 minutes small break, and after that we will resume the remaining session. Okay, let's start with the remaining session. So here the question says that this is on heat capacity equations, and this is question number 8, and it says that specific heat ratio is expressed as ratio of isentropic compressibility to isothermal compressibility of substance. So this is question number 8. So it says that isothermal compressibility and then isentropic compressibility. Isentropic compressibility. So this is kappa and this is alpha. Okay. So we know that what it is asking the specific heat ratio is dou P by dou V at constant entropy divided by dou P by dou V at constant temperature. Okay, so this is what is. But then we know that kappa equals to 1 minus 1 by specific volume constant T. This. And also alpha equals to minus 1 by nu dou by dou P of nu at constant entropy. In that case, implies K equals to, or you can also write minus K, dou V by dou P at constant T, right? And here you can write minus alpha nu dou P at constant S. Okay. So using, if you say this is 1, this is 2 and this is 3. So if you use 2 and 3 in 1, use 2 and 3 in 1. In that case, we get, what do we get? We get Cp by Cv equals to kappa by alpha. This is what we get. So which is basically isothermal compressibility by isentropic compressibility. Isothermal by isentropic, right? But the question says that isentropic to isothermal, which is opposite. Sorry. So in that case, this becomes a false statement. Okay. Now moving on to for the next question. So this is question number 9 based on heat capacity equation, and it states that for substances with negative value of beta, that is volume expansivity, the isothermal increase in pressure causes heat absorption. So whether this is true or false. So isothermal compressibility is with respect to pressure change, the change in specific volume, and volume expansivity is with respect to change in specific volume with respect to temperature. Okay. So in this case, pressure remains constant. That is volume expansivity. So for substances with negative value of beta, negative value of beta means if temperature we will increase, the volume will decrease. Okay. Because beta is 1 by mu. This is your beta, volume expansivity. Right? So if it is negative, so in that case, for such substances in which with constant pressure, if we increase the temperature, the specific volume will decrease. Okay. The isothermal increase in pressure causes heat absorption. So if in such a substance, if at constant temperature, pressure is increased, in that case, what will happen to heat absorption? Whether it will be, well, what will happen to heat, whether it will be absorbed or rejected. So substances which have negative value of beta are rubber. For example, rubber is one such example. So in such substances, if isothermally pressure is increased, this leads to heat absorption. Okay, this is a true statement. So option A will be correct. Let's see the next question, which is question number 10. So this question states that from heat capacity equations only, the reversible adiabatic increase in pressure will produce an increase of temperature. So this is now a reversible adiabatic process. Okay, in which increase in pressure will produce an increase of temperature for a pure substance with positive value of beta. and vice versa. So positive value of beta means with increase in temperature, the specific volume will increase. Increase in temperature, specific volume will increase. Okay. For example, gases. If you increase the temperature, the volume, specific volume will increase. Sorry. Okay. So in that case, if the pressure will increase, then the temperature will also increase. This is for substances which have positive beta value. Okay. So, and if the value is negative, in that case, temperature, if you increase the pressure, temperature will decrease. So whether the statement is correct or not. So this statement is correct. Okay. So this is from this question has been framed from case 2 of TDS equations. The next topic is on throttling process. Next question is on throttling process. Sorry, and this is question number 11. So this question states that when a fluid passes through its restriction, its pressure dash, and this pressure is dash, and this phenomena this phenomenon is known as dash. So this basically is the definition of throttling process. Okay. So in throttling process, as we discussed in the topics briefly, that because of restriction, there is increase in pressure. Sorry, decrease in pressure. Sorry, a decrease in pressure, and this also leads to change in pressure of the substance or the fluid, which is undergoing throttling by means of some device. Okay, so in that case, C option will be correct. So this is decreases and it is throttling process. So this was question number 11. So we now have question number 12 again on throttling process. So this question number 12 states that the magnitude of temperature drop Okay. So which is the coefficient that governs the temperature drop? Is this throttling coefficient because it's a throttling process, or it's a liquefaction coefficient because after the inversion state is crossed, there is liquefaction of gases, or it's a Joule-Thomson coefficient, or is there anything like Clapeyron coefficient? So the answer to this question is C. Okay. So we have defined Joule-Thomson coefficient here, if you see. So this is basically the change in temperature with change in pressure. The pressure change that the fluid experiences while it's throttling. Okay. So C is the correct option to this question. So moving on to next question. Which is again based on throttling process. So this states that in a throttling process, the dash of the fluid remains constant. We have seen that in a throttling process, or a throttling process is an isenthalpic process. Okay. And in it, there is no change in enthalpy. Though there is change in pressure, there is change in temperature, but the enthalpy remains constant. There is no loss of enthalpy in this case. So in a throttling process, the enthalpy of a fluid remains constant, which is option number B. Okay. So moving on to next question. So this question is on inversion curve. Okay. This is an interesting topic. Inversion curve, throttling, liquefaction of gases. These were interesting. So question number 14. It states that The slope of an isenthalpic curve at any state is the Joule-Thomson coefficient. So we have seen this. The slope of an isenthalpic curve is at any state in the TP diagram. This is the Joule-Thomson coefficient. So Joule-Thomson coefficient essentially is dou by dou P of T at constant enthalpy. So the question has mentioned that the curve is isenthalpic, okay, and this is a TP diagram. So in that case, this matches statement matches with Joule-Thomson coefficient, okay. So this becomes a correct statement in that case. Now moving on to next question. This is a correct statement. Please try to answer this. So we can see the graph, okay, the inversion curve we can see. So this is our inversion curve, and looking at this curve, we can try to answer the question. So can the Joule-Thomson coefficient be negative in any case, or it will always be greater than equal to zero? So if we see this curve, we can see that. So if we take inversion state as our reference, to the right of inversion state, if you see, the slope of this curve is negative, right? And then to the left of this inversion state, the slope is positive. Okay. And at the inversion state, the slope is always zero. Okay, because it's a transition state. So based on the curve, it can be said that the Joule-Thomson coefficient can either be positive or zero or negative. Okay. So if the statement says that the Joule-Thomson coefficient can never be negative, in that case, that is not a correct statement. So the Joule-Thomson coefficient can never be negative. False. It can be negative. Okay. From where the fluid starts to throttle. At first, the temperature increases, and beyond the inversion curve, this temperature decreases, right? And when it starts to throttle up till the point of inversion state, the coefficient remains negative. Okay. So if the statement says that it can never be negative, then it's a false statement because it can be negative, or it is negative in the initial stages. Again, a question on inversion curve. This is question number 16. So we have two conceptual questions left after this. And after that, we will have four numerical questions to solve. And then we will end the session. Okay. So I've just mentioned it that at an inversion state, the value of Joule-Thomson coefficient is zero. Okay. So option A is correct. So moving on to next question, question number 17. This again is on inversion curve, and it states that for isenthalpic curves, having an inversion state, the temperature at the exit of the apparatus is always greater the initial than the initial temperature. We can try to answer this. So for isenthalpic curves having an inversion state, the temperature at the exit of apparatus is always greater than the initial temperature. So this is not the case. Why? Because if we go to the left of inversion state, right, there are cases where the temperature at exit is less than the temperature at inlet, okay, at the starting. But also there are cases where temperature at exit is greater than temperature at inlet. So it can be both ways. So if such an extreme statement is passed, that the temperature at exit of the apparatus is always at the exit is always greater than the initial temperature, then this becomes a false statement. So this is B option. Now moving on to the last conceptual question. Liquefaction of gases. So this question states that this is on liquefaction of gases. The liquefaction will be maximum when the value of enthalpy of entering gas is minimum. Whether this is correct or not. Please try to answer this. So this can be derived from this thing. Okay. Which thing? This is question number 18. So if you see, let's say at initial stage, there is an enthalpy of Hi, okay, and at final stage, some part been has remained as gas and some part has converted into liquid, okay, and the enthalpy corresponding to these two phases is given in this way. And the part in which liquefaction takes place, let's say that is Y, okay, and the part which remains in gaseous state is 1 minus Y, right? So because it will be isenthalpic process, in that case the enthalpy of initial and final stages will remain same, right? And if we try to work this out, we see y comes out to be okay. So if liquefaction has to be maximum, that is y has to be maximum. In that case, we see that hi has to be minimum, right? So initial enthalpy has to be minimum. When the enthalpy of entering gas is minimum, which is one and the same thing. So this becomes a true statement. So now we are done with the conceptual questions for this session number 5, and we will solve numericals now. So this information is common information given for numericals from 19 to 22. In it, we have the vapor pressure of solid ammonia is given by LNP equals to 22.06 minus 3724 divided by 2 divided by T, and the vapor pressure of liquid ammonia is given by LNP equals to 18.22 minus 2992 divided by T. Okay, so these vapor pressures have been given. Okay, now assume the volume at saturated vapor state is very large in comparison to volume at saturated solid state. This has been given. So based on this, we will solve this question, these questions. So first question is, what is the temperature of the triple point? So what happens is, at the triple point, at the saturated conditions, these two pressures can be equated. Okay, this is question number 19. So for solid state, this is given as LNP equals to 22.06 minus 3724 by T. And for liquid ammonia case, this is given as LNP equals to 18.22 minus 2992 divided by T. Okay, so these at saturated conditions, these two can be equated, which implies 22.06 minus 3724 divided by T equals to 18.22 minus 2992 divided by T, which essentially means 3.84 equals to 732 divided by T. That is temperature equals to 190.62 Kelvin. Okay. So this is our question number 19. Then question number 20. We'll solve question number 20. So question number 20, what is question number 20? So this asks for latent heat of sublimation. Okay. So sublimation is direct from solid to what? Solid to vapor. Okay. So for this we will use Clausius-Clapeyron equation. Okay. So Clausius-Clapeyron equation gives you d by dt of p, and we have here for solid state ln p equals to 22.06 minus 3724 by t. And if we differentiate on both sides, what we get is 3724 divided by t square dt implies dp by dt equals to 3724 divided by p by t square. Okay, this becomes 1 in this question. Then we can use Clausius-Clapeyron equation because volume at saturated vapor state is very large than volume at saturated solid state. That we saw is one of the assumptions that we made while we changed our Clapeyron equation to converted our Clapeyron equation to Clausius-Clapeyron equation. And then Clausius-Clapeyron equation says that dp by dt equals to p by rt square L of sublimation, right? And we equate 1 and 2, we get then this becomes 3724 into R into 8314. So this comes out to be 30.96 megajoule per kg mole. Okay. Then your question number 21 is there. It says that latent heat of vaporization. So liquid state we have, which is ln p equals to 18.22 minus 2992 divided by T. In that case, if you differentiate both sides, dp 1 by P equals to 2992 T square implies dp by dt equals to 2992 E by T square. Okay. And then from Clausius, dp by dt equals to P by R T square. So this is your 1, this is your 2, 8, 1 and 2. And we get 2992 P by T square equals to P by R T square L vaporization. So this L vaporization is equal to 2992 into R into 8314, which is 24.87 megajoule per kg mole. So this is your question number 21. And now the last question, which is calculate the latent heat of fusion at the triple point. So fusion is solid to liquid. So we have latent heat of sublimation and latent heat of vaporization. Okay. So latent heat of sublimation includes latent heat of fusion and latent. So this is latent heat of sublimation equal to latent heat of fusion plus latent heat of vaporization. Implies latent heat of fusion equals to latent heat of sublimation minus latent heat of vaporization. So this comes out to be 30.96 minus 24.87, and this is equals to 6.09 megajoule per kg mole. So this was our last question of this session, and with this we come to the end of this session. Okay, so I'll just conclude. So this particular session had discussions and questions on thermodynamic property relations. Thermodynamic property relations basically pertaining to heat capacity equations and throttling process. Okay, so in throttling process, we also see how the liquefaction of gases can take place beyond the inversion state, from where the temperature starts to decrease. Okay, but then also there is a concept of maximum inversion temperature. So if the initial temperature of the fluid is greater than this temperature, in that case liquefaction is not possible. Okay, so uh, these are the topics. And then in conceptual questions, we discuss 18 questions based on these concepts only: throttling process, liquefaction of gases, then there's heat capacity equations, right? And then in starting, we discuss evaluation of property change topic, questions based on this, right? And this way we did 18 conceptual questions, and after that we moved on to numerical questions. And in this section we did four numerical questions based on the phase change process. Okay, so solid to liquids, liquid to gas, or directly solid to gas. Based on this, we performed numericals. And this way, we have come to the end of this session. So for this session, I have this much only, and we shall meet again for the next session, uh, session number 6, in the coming Sunday, and the timing will remain from 3 to 5 p.m. Until then, I'll say goodbye and happy learning. Thank you.